ladies and gentlemen, dear colleagues. It is my great pleasure to introduce the inaugural lesson of Professor Dimitrios Lignos. As you may know, we had planned for two inaugural lectures tonight. Unfortunately, Paolo Tombesi is very sick and will not be able to come today. He very regretfully had to cancel this morning, seeing his state. So we will have the whole spotlight on our colleague Dimitrios Lignos. So thank you very much all for being here. And let me say a few words about our distinguished professor before I pass him the floor. So Dimitrios Lignos has started as associate professor in ENAC on January 1st, 2016, so a little over 1 year ago, by creating his own lab called the RESSLAB, which stands for Resilient Steel Structures Laboratory, but also integrated the existing steel structures lab, known as ECOM, as well as its team, and notably Professor Alain Nussbaumer, who is also with us tonight. At 37 years old, Dimitrios Lignos has already a very rich academic career behind him, remarkably prolific in publications and awards, which I will not be able to go through, but I will give you a little bit of an excerpt. He has made a name for himself internationally through large-scale experiments in the field of structural engineering. His work focuses on the development of performance-based assessment techniques and the use of integrated experimental and analytical methods for the seismic design and risk assessment of steel structures around issues that he will tell us more about, but some of the keywords that we got out of his different papers is issues of collapse, of risk assessment, of seismic resilience, multi-hazard mitigation, and earthquake engineering. So these are all part of his large expertise. He's also developed a series of tools that have been made available to the public, such as his web-based interactive tool for performance-based earthquake engineering that facilitate nonlinear component modeling of steel connections, and as well as fragility curves, and has a fully searchable structural component database. In terms of education, he graduated in 2003 at the National Technical University of Athens in Greece with an engineering degree specialized in structures. Then, with the support of a Fulbright scholarship, he did a Master of Science at Stanford University in 2004 in Civil and Environmental Engineering, followed by a PhD at the same institution and under the same supervisor, late Professor Krawinkler. After two successive postdocs at Stanford and at Kyoto University, he came back to Stanford as a researcher before being appointed in 2010 as assistant professor at McGill University, Canada, where he made an early tenure in 2015 and in fact joined us shortly afterwards at EPFL. He's the recipient of numerous awards that are far too numerous to cite them extensively here, that already started in his very early career as an undergraduate with several medals and recognitions for being an outstanding student. So amongst these many awards, I would like to pick the Medal and Award for Exemplary Research in the area of earthquake engineering that was awarded during the 3rd Conference on Mechanics and Solid at MIT. He was also the first recipient for John A. Bloom Fellow for Doctor of Philosophy at Stanford, where he did his PhD. He was twice the ASCE Outstanding Reviewer Award in 2012 and 2013 in recognition of his outstanding service as a reviewer for the American Society of Civil Engineers, Journal of Structural Engineering. He's also gotten the ASSCE State of the Art of Civil Engineering Award in 2013 for a paper entitled Deterioration Modeling of Steel Components in Support of Collapse Prediction of Steel Moment Frames Under Earthquake Loading. He also got the Christophe Pierre Award for Research Excellence Early Career that recognizes excellence and potential for future preeminence in research by the academic staff in the Faculty of Engineering at McGill. the William Dawson Scholar Award for Infrastructure Resilience, also at McGill, and he notably also recently joined the Canadian Standards Association S16 Steel Structures for the Building Technical Committee, where he will contribute and work on the next revision of the CSA's S16 seismic provisions. So with this long list of achievements, I would like to wish him to continue in this very successful path for the future with us at EPFL, and wish you a lot of pleasure with your research, teaching, and collaborations within ENAC and at EPFL. The floor is yours.
Okay. Well, thank you, Marlene, for the very nice introduction. And also, I'd like to thank you for being here at this time. It's a pleasure for me to be here at the EPFL. And let me actually switch. Okay, so what you will hear today is related to a collapse risk assessment of steel structures, some accomplishments, in part what you heard a bit from Professor Andersen, and also some future challenges, which is related pretty much to what we do here at EPFL. Okay, so before I start, I'd like to say that during the last U.S. presidential inauguration, the drivers in Maryland highway were actually informed that they should expect delays, so don't expect delays in this presentation. It will be around 35 minutes. And they also considered to go to Canada as an escape. Hopefully, what you are going to hear at the end, you won't want to escape to Canada. So, with that, I'd like to, before I start, to acknowledge my research group, both at McGill, but also a few people are actually here from McGill. A number of them have positions in academia, others have prestigious positions in a high-profile industry, and without them, what you see today is not going to be possible. It wouldn't be possible. Okay, so with that, I'll give you a little bit about motivation behind what you will see. So, what we really do is engineering, and so engineering is the art of modeling materials that we do not wholly understand into shapes we cannot precisely analyze, so as to withstand forces that we cannot properly assess in such a way that the public has no reason to suspect the extent of our ignorance. Okay, so but we still have to design innovative structures that are challenging from architectural point of view and also from structural point of view. And a few examples you see on the screen, like Guggenheim Museum, International Tokyo Forum, very challenging bridges, and also that there is some kind of worldwide competition in terms of what's the tallest building in the world. And if we are dealing with such systems, we need tools that we can assess their performance, because there are uncertainties, and we have to make sure that stability issues or collapse, you'll hear a lot about this, won't happen. Okay, talking about loads, so in the past years we have witnessed a number of events that essentially forces exceeded what we design our structures with, based on regional seismic provisions. And obviously in this case, what could happen is the collapse risk becomes critical. You have here several examples of buildings that collapsed because of this difference between what we designed them for and what they actually experience. So again, the point is that we need to have simulation tools and metrics so that we can know the ability of structures to withstand a given level of demand without suffering severe deterioration, because obviously we would like to make sure that people, stay safe, and no matter what the disaster is, obviously, we have to make sure that we don't have casualties. Now, suppose that you don't have casualties, which is obviously the number one thing. You still have to also encounter losses after a natural disaster, And this is an example for a scenario, for instance, in Canada, that if a 7.1 magnitude earthquake occurs, this will result to about 61 billion in damage, and only 12 billion will be reinsured. Okay, so under new regulations, by year 2022, insurers in Canada must be capitalized for 1 in 500-year earthquake. And if you think that this is just stories so that you can go and buy insurance, it's actually not, because if you look at New Zealand in 2011 with a 6.3 earthquake, what happened is no casualties, but total cost to insurance for rebuilding was approximately 40 billion. That corresponds to 20% of New Zealand's GDP. Okay, so with these things in mind, what we want to do is we would like to develop, or what we are trying to do is we are trying to develop a simulation framework for a collapse risk assessment of steel structures that incorporates a number of features. One of them is considering uncertainty, both in the hazard but also in the model, can facilitate the implementation of new design practices. For instance, if you have developed a new system or new materials, the question is how you promote resilience, so how you promote the ability of a structure to act and rebound under catastrophes. Okay. Also, we are dealing with critical facilities that they have to maintain functionality. These are hospitals or could be nuclear facilities, that they are not necessarily steel structures, but again, the point is that you have to validate the efficiency of innovative technologies so that you minimize the risk and maintain functionality. And at the end, what we do, we have to keep in mind that we have to communicate it to stakeholders, owners, and policymakers, so that we can take informed decisions for risk management, also preparedness, and response after natural disasters. Okay, so in line with what I presented, what we've done is we've developed a framework for a collapse risk assessment of steel structures. I'm going to show in a nutshell. So that framework consists of models that they are non-linear, of course. In order to validate these models, we do carefully designed experiments. You will see a few of them. Sometimes, component experiments are not enough, so we are doing also large-scale testing or full-scale testing. And then, if you bring in your hazard, so if you are in the US or like Switzerland's a moderate seismicity, and you have a particular building that you want to evaluate, with these tools, we actually conduct rigorous nonlinear response history analysis. We come up with damage functions that are expressed in a probabilistic way. And because at the end you have to communicate this to an owner that doesn't necessarily understand what damage means, we also bring in the aspect of economics. Okay, so basically we try to express, what losses, what kind of expected losses we should see under this particular event. So this framework, this is the only equation, is also known as the Cornell-Kravwinkler equation. It's a triple integral that essentially combines the hazard, structural analysis, damage analysis, and at the end losses. So what you will see today is basically focusing on the enhancements we are doing are related pretty much to these three brackets. So engineers probably are interested about structural analysis, damage analysis. Insurers, owners, and so on care about losses. So obviously, that covers everything. Now, before I get into the specifics, let me just give you one slide so why structures collapse. So this is a collapse test that was actually, the test happened in 2013. And if you take a snapshot here, you see what's really happening. If you have a design level intensity earthquake, what we will actually see is that, because of the loads that are transferred in the system, your beams will fail and your columns will practically remain elastic. So that's what we do when we design structures in seismic regions. Okay. Now, when the earthquake becomes larger, this is something that we don't really know up front. What happens is you get instabilities. Okay. So instabilities cause force redistributions, and then what happens is that the members that maintain stability, these columns, are actually damaged. So if you damage the columns, eventually you will lose the stability of the system. So it's that simple. Okay, so it's not that simple, but with that slide you can probably get the big picture of it. So what we need to do is that if we want to assess this performance and if we want to actually improve it, what we do is we develop models. Models could be fairly sophisticated or could be simpler. In this particular case, developed column models that take into account residual stresses, instabilities, material nonlinearities, and so on. And then, hopefully, if you have a test, you can see if your model corresponds to reality. If you don't have a test, what we normally do is we invest on facilities, like similar to one that we have here. And we did that in the past few years. We allocated substantial resources to design and expand testing facilities to understand the behavior of components at large deformations associated with structural collapse. So you see here two particular facilities in Montreal. And what we do with those is we actually test components the way we didn't test before. This is an example of a column. It's a full-scale column that if you actually look here at the base, you will see, what's the damage progression during a cyclic loading. And what you will soon see is that the column eventually loses stability because of geometric issues associated with local buckling. One thing that is striking is that in this particular case, what we learned is that columns, when they lose stability, they also move vertically. So the floor above the column supports also comes down, and obviously that's not good when you are dealing with collapse. Again, we've done numerous testing. I'm not going to show everything to understand the member behavior after instabilities occur. And what we do with that, as Professor Anderson mentioned, is we have actually developed databases that we have systematically collected whatever test is available in the past 50 years in key structural components associated with steel structures. These databases are available, or will soon be available from the RESSLAB webpage. But technically what you do with this is that if you are interested about a particular component, what you are doing is you come in, it's a fully searchable interface as you do with Google. You can search for whatever data you are interested, beam, column, braces, whatever. It interfaces with elements that we particularly develop, but it can interface also with your elements. And by doing optimization, I have it as a black box. We calibrate the models. Eventually, simulation looks reasonably close to the model. Now, provided that we are happy with this, what we've done is that we have been working with open source platform that was originally developed in the late 90s at Berkeley, namely OpenSeas. And what we are doing here is that, if you have a structure and you want to model a column, you can actually use one of the elements that we have developed, and we have implemented in that platform as a class, an element class. If you are working on numerical techniques, integrators, you can also come in a different class actually do that. Or if you are looking at other particular elements, in the same manner, we have actually implemented all this in that platform. Now, if you put it all together, what this platform allows us to do is that we can actually do collapse simulation of actual structures. So this is an illustration of an 8-story building. It's a steel structure that is experiencing a fairly large earthquake. You see that the system develops substantial lateral deformations, and eventually the system loses stability because its story force becomes equals to 0 at very large deformations. Okay, now people are skeptical when you talk to them about simulations. Okay, so sometimes you have to do extreme things to demonstrate that the tools you are developing actually work. Okay, so this is one of the extreme things. So this is a full-scale test of a 4-story building that is experiencing the 1995 Kobe earthquake. So what's happening here is that the four-story structure develops a first-story mechanism, and the reason is that if you actually look at the first-story columns, essentially the columns yield, buckle, and damage is concentrated there, and the system collapses. So we actually, if you look at the comparison of tests versus simulation, the predictions corresponding to lateral deformations of the first-story drift they are, reasonably close. So that, gives us confidence in what we are doing. And, when we go out there and say that particular structure, the collapse risk is high, I mean, we can demonstrate comparisons like this to actually make sure that, people believe us. Obviously, this is not the only thing. We've done several tests, nearly full scale on systems and subsystems in order to evaluate techniques that, if collapse is an issue, how we prevent it. So this is an example that we actually did at Richmond Field Station at UC Berkeley. And this is, again, something different that we recently did at Buffalo. Now, again, all this is good. The question is, what do you do with it? So, what do you do with it is that we work with NIST, the National Institutes of Standards and Technology, so that we will soon have modeling guidelines and acceptance criteria for nonlinear modeling of structures, of steel structures. And this document will be available from pretty much late this year. The other thing we are interested is that to make sure that people use our simulation tools, so we keep track, because as our dean said, we actually provide everything. We have everything publicly available. So what we do here is that we keep track who is actually using the simulation models or interactive tools, and as well as the data that we have developed. And as you see, pretty much we have about 50,000 users around the globe. About 50% is in the US. The rest is pretty much in other continents. There are some gray areas here, but it's for obvious reasons. Obviously, we don't build structures where you have polar bears. Now, so introduced to the framework, I told you the basics, and I guess some big picture issues. So let me show you a few examples that we've used this to improve standards and also promote innovative techniques for retrofit. So the first one, this is a study we did with my first PhD student, who's actually here as a postdoc. We evaluated the collapse risk of steel structures designed in Urban, California. Obviously, California is a high seismicity zone. The design codes, we claim that, they're fairly sophisticated and, collapse shouldn't be an issue. So we actually use a portfolio of buildings that, are typically designed in downtown LA. And if you use not just one ground motion, but, a bunch of them so that you can do statistics, we developed damage functions for these particular structures. So if you know the intensity of your earthquake, if you have, for instance, a 4-story building designed in this location, the probability of collapse is 10%. If you have a 12-story building, probability of collapse goes up to 70%. And the question is, how do you transform this to if it's acceptable or not? Okay, so we've developed some metrics. I'm not going to go into the detail. So these metrics, essentially what they do is they translate the risk over the life expectancy of the building. Okay. So, for instance, in this figure here, what you see is that the collapse risk over 50-year building life expectancy. Okay, and you see that if you live in a 4-story or if you work in a 4-story building in LA, the collapse risk is 2.5% over 50 years. So the question is if that's big or small. So if you look at the current limit code says that you cannot accept more than 1%, so obviously it's bad. So if you design the buildings according to the today's standards, you have that risk. We actually propose design modifications in specific, we call them capacity design principles. And if you actually change the, or refine the code, you can actually reduce the risk less than 0.5%. Okay. Now, which is actually good. Now, the other thing that, we are doing with this is that, how do you achieve what we call resilience or seismic resilience in critical facilities? So here you have two examples that we actually have looked at carefully. One is existing medical facilities in Canada. Okay, Canada is a moderate zone. If you are, for instance, in Montreal, it's a moderate zone. Probably, the seismicity fairly close to what you see here in Switzerland. We also evaluated the risk in tall buildings. These systems, because they were designed in the late 60s, they were designed without seismic considerations. So collapse risk is high in this case because we are getting failures that are not supposed to happen. Okay, so I'm going to talk about the hospital. So we use the same platform I showed you. We modelize it in pretty much the way we do. So we assess the collapse risk under a scenario earthquake event because the client wanted to make sure that, if collapse is an issue, and then, what can we do? So obviously, collapse is an issue under scenario earthquake, and this is a hospital. If you have a natural disaster, you want to make sure that the hospital is functional because if you are injured, you want to make sure that you can go to the hospital. Okay, so what we did is in order to achieve resilience, like meaning continuous functionality, we actually retrofitted the system with what we call a seismic isolator. So what this does is on your right is your medical facility under, with no retrofit. So obviously you see that, structure sees excessive damage. If you are in the structure or if your equipment is in the structure, will probably be damaged. On the left, hopefully, all the deformation has been picked up by the device here, and pretty much everything inside remains operational. Okay, so we actually designed that system, and we actually evaluated in the same simulation platform that I showed you. And what you see here is the case with no retrofit. This picture shows the lateral deformations of your system with no retrofit, and with blue line is the client design requirements. So obviously, we fail a lot client design requirements. On the right, you see what's happening if you actually retrofit the system. And obviously, in almost all cases, we respect the client design requirements, also on average, but also on 90th percentile or close to 100% success. So client bought it, but we had to make sure that we convince him in a way that not a structural engineer understands. So in a way that, you have to show him the finances. So the finances, so what we did is we've developed a loss estimation toolbox that actually is an add-on on the simulation platform. And what you can do with it is that if you know the expected deflections, forces, and so on, you can actually compute the expected losses under a scenario event or under a real event. Okay, so on your left here, you see the normalized expected losses under the scenario earthquake with no retrofit, and consider that the total replacement cost of the building is 400 million. Okay, because you have to count also the medical equipment and so on. Okay, now on the right, you have the case with the innovative retrofit system. So you see that, no retrofit, you should expect more than 85% of your replacement cost to be spent on repairs. Because, for instance, if you are in this room, an earthquake happens, the ceiling comes down, projectors fall apart, this corresponds to money that you have to actually take into consideration for replacement. Okay, so if it's a medical facility and you have an MRI device that is damaged, that costs a lot of money. So obviously, this adds up a lot. Okay, so risk goes down, also the dollars go down, and this is something that, people can understand easily because structural engineer knows about forces, displacements. Unfortunately or fortunately, the owners or policymakers, they understand about finances, and that's the point. Okay, so we made the connection. Now again, there are several examples I can show you, but I'm not gonna do it. So what we did is we used some of these cases to improve our North American standards. Hopefully we can do this in Europe now that we are in Europe, including the Canadian code, the American code, both for new and existing buildings. Some of these documents will come out in the next year or so. Okay. Now, with that in mind, I'd like now to focus a little bit on some current and future things we are doing here at EPFL. So this is not all about teaching, this is not all about research, it's also about teaching. Okay, so what we try to do quickly meaning, in a short time, we try to implement courses that, we think is essential so that, some of these concepts you saw in graphs and videos, the future engineers can actually consider. One of them is an undergraduate class related to structural stability. So on the left, you see a test we did. On the right, we have this kit MOLA that we actually illustrate the concept of buckling, and students understand it better. Okay. We also developed a master's class related to advanced steel design. We offer an online recording module because, students sometimes, they want to adopt the material at their own pace. Currently, we have given 11 semester projects in the past 1.5 years or so. Some of them are conceptual. We are actually utilizing tools that we have from ENAC to demonstrate concepts with stability. But also we use the interactive tools that we offer online to assess the risk of existing schools in Switzerland due to earthquake and fire that haven't been designed for earthquake consideration. And if you have a moderate event, something could happen. Okay. Now, in terms of research, I've been recently awarded the Swiss National Science Foundation project that essentially expands what we've already developed. And in particular, it combines it with, so it combines high fidelity modeling with, let's say, innovative experimental testing, in which that you can combine actually experimental assembly and a numerical assembly, and you can actually assess the performance of a large system that you won't have the chance to do it unless if you have like a huge shake table. Okay, so with that, we'd like to assess the performance of composite systems. We plan to host a blind analysis contest that we will advertise worldwide to assess modeling capabilities for composite systems. And we also like to develop innovative components to achieve seismic resilience of steel structures. We also, same project involves some thermal loading effects to be considered. So we are designing a multi-purpose setup for our lab here that we can actually apply both mechanical and thermal loading in assemblies or systems so that we can understand better what the stability concerns could be if you actually have thermal loading. Okay, now, if this goes well, hopefully it will, the point is that, we expand in a few years from now to address, bigger problem or like bigger issues, so, having, the principle being the same but changing the hazard. Like for instance, if you are dealing with wind turbines, the hazard obviously is not earthquake, or could be earthquake, but it's also wind. So if you change your hazard, again, you need a numerical model for the turbine. Again, you need ways to translate it to damage. So again, as long as we are comfortable with this, we can extend it to this. Also, we can look at risk of, fairly challenging problems related to risk of debris in space structures. Like, this is a serious problem that could actually cause stability and collapse associated issues. Space structures in part could be steel, in part could be composite, in part could be something else. Obviously, this is something that it is worth more investigation. Now, the other thing is that, we are approaching collapse through materials intelligence. So we are very close to form a research agreement with the second biggest steel-making company in the world. This is Nippon Steel, to actually further develop materials that have high potential for collapse risk mitigation. So these are thermomechanically controlled processing materials that essentially what you could do with them is that you can easily increase their strength. At the same time, you can maintain their plastic deformation at very large levels. This is actually related to an ENAC exploratory grant that we were happy to receive with Jean-François' lab in October 2016. So now it looks like, things are moving forward. We still have to do some work on it, but I mean, the point is that, the industry is interested, and that's interesting. Now, the last thing is, again, so far what I showed you applies to particular buildings. So building, or, if you have a bridge, we are looking at a certain bridge and so on. But obviously, when we are studying this, we are interested about, the city level. Okay, so we are using sensing data to extend our simulation framework to at the city scale. In part, we have been successful. I'll show you one example. And the reason why we need this is because, like this, you can do a disaster risk management. So if you have sensing data from a building, this data could be from sensors or could be coming from your computer, because your computer normally is stationary, it's like at a certain location, or could be from your cell phone, but that's more complicated because you could also be moving if an earthquake comes in. And then suppose we have access to this data, we can analyze in the computer cluster. We have also written an Android application that does actually system identification and is able to reasonably close predict what a building could do if you're inside that building. And then by using non-model approaches and model approaches, we can actually develop what we call generalized city-scale damage maps. If we have information from building information modeling, in particular, we are interested about building assets, and this information is normally available. We can actually assess losses. We can also collaborate with social scientists in a sense that, we can understand what people will do in the case that, you can predict what's happening at the city level. And then you can plan better your evacuation or response, allocate better rescue resources and so on. This is an example, something we did recently for the city of Los Angeles. From an earthquake that actually happened in 1994, Northridge earthquake. So we used data from instrumented buildings. We computed the expected losses at a city scale, and this we could do within minutes. Okay, so having that, if you add up the losses in steel buildings, they were in the range of 5 billion. According to the surveys, this was in the range of 7. So obviously we were under-predicting, but of course, this is a first estimate so that you can see, what the big problem is and, where it's concentrated. In this case, could be here or around here. Okay, so with that, 32 minutes. Okay, so with that, I'd like to conclude the talk. So achieving resilience of engineering facilities and cities, this is the next challenge. Obviously, there is still much work that needs to be done. If you ask me how, I will actually respond to you in the way I learned here at ENAC. So I look at the affinity map. Let's see, how we can collaborate, and I'm sure we can come up with great things. So with that, I'd like to acknowledge sponsors, and also I'd like to thank you for your kind attention, and I'll be happy to take any questions in case that you have. Okay, so thank you. Yeah.